So good morning, distinguished colleagues and guests. It's November 18th, 2021, 11 a.m. Moscow time. And we're beginning the panel session for the defense of the thesis by Alexander Oleynichenko. The thesis is submitted for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 133, theoretical physics. The topic of the thesis is relativistic coupled cluster theory for electronic states of molecules with several open shells. Under the order issued by the Academic Secretary of St. Petersburg State University as of August 14th, 2021, as of August 24th, 2021, number 8190/1. I, Oleg Andreev, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Quantum Mechanics of St. Petersburg State University, was appointed the Chairman of the Board. The order also approved the members of the Board, namely Ivan Mitropolsky, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Nuclear Physics Research Methods of St. Petersburg State University, Mikhail Kozlov, Doctor of Sciences in Physics and Mathematics, leading researcher at the Konstantinov Institute of Nuclear Physics of the NRC Kurchatov Institute, Vladimir Yerokhin, Doctor of Sciences in Physics and Mathematics, Chief Researcher at the Center for Advanced Studies of Peter the Great Polytechnic University. The following members of the board are working remotely today: Alexander Peterhof, Doctor of Sciences in Physics and Mathematics, Associate Professor of the Konstantinov Institute of Nuclear Physics of NRC Kurchatov Institute. And he's also Associate Professor at the Department of Quantum Mechanics of St. Petersburg State University. Do you hear us? Yes, I do. Okay, the answer is yes. Alexander Trofimov, Doctor of Sciences in Chemistry, Professor of the Russian Academy of Sciences, Professor of the Department of Physical and Colloidal Chemistry, leading researcher of the Laboratory of Quantum Chemical Modeling of Molecular Systems of the Irkutsk State University. Do you hear us and see us? Alexander Borisovich? Yes, yes, I do. Okay. Mariana Safronova, Doctor of Philosophy, full Professor of the University of Delaware, the United States of America. Mariana, do you hear us? Yes, I do. And we also have our candidate for the degree, Alexander Vitalyevich Oleynichenko. And also remotely we have the thesis supervisor, Andrei Zaitsevsky, Doctor of Sciences in Physics and Mathematics, leading researcher of the Faculty of Chemistry of the Lomonosov Moscow State University. And I would also like to inform you that the panel session of the Dissertation Board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted from Russian into English and vice versa. And currently we have an email address posted on the page with live broadcast of the board session. And all listeners can submit their questions to Mr. Oleynichenko online. The questions regarding the thesis or scientific discussion or the speech of the applicant. And thus they can participate in our scientific discussion. These questions will be forwarded to me by our technical service, and I will read them out during the discussion. The questions must be related to the presentation of the candidate for the degree and to the content of the thesis. And do not forget to give your name and position if you submit a question. The questions that have nothing to do with the scientific discussion or the text of the thesis or anonymous questions will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University approved by local normative acts, the session of the Dissertation Board is valid providing 2/3 of the appointed board members are present. And the total number is not to be fewer than 4 people. Our board consists of 7 people. Everyone is with us today remotely, including 3 members of the board who are working remotely. And we have a multimedia connection with them, therefore we have the quorum. And I ask the representative of the Department of Dissertation Board Support to fill out the attendance list. And our session should not last more than 2 hours, and the agenda is as follows. First comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements, followed by chairman's replies to questions, if any. Second, the candidate's presentation providing an overview and findings of the research, 20 minutes for that. Third, questions to the candidate regarding the presentation, 2 minutes per question. Then candidate's replies to the questions, 5 minutes for all. Fifth, the reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions to the applicant. 10 minutes each. Sixth, the chairman's report on the thesis, 10 minutes. Then, the candidate's comments about the reports on the thesis and replies to the questions, 20 minutes for that. Then, open discussion, speeches by those present at the defense with a brief presentation of their positions or questions or suggestions to the candidate on the topic of the research. 2 minutes per person. And do not forget to state your full name, academic rank, position, and place of work in the registration list. Then, the chairman will ask questions submitted during the broadcast via our website. And I would like to draw your attention to the fact that the written questions that will take more than 10 minutes to read out will not be voiced. Then the candidate's replies to the questions, if any. Then the presentation of the candidate's thesis supervisor, 3 minutes will be given for that. Then we're going to have a 5-minute discussion before the open balloting on conferring or non-conferring the academic degree, and the discussion of the results of the defense is not broadcast. Then we're going to have open balloting. We count the votes and record the results in the protocol. Next, we're going to make a decision on whether to confer the academic degree or not. And finally, we're going to listen to the candidate's closing speech, no more than 2 minutes for that. So, distinguished colleagues, any questions or objections on our agenda? Okay, if there are no questions or objections, let us proceed. But before we do that, I kindly ask you to switch off the sound on your mobile phones. Thank you. So, let us proceed. The chairman's presentation. A thesis by Alexander Vitalyevich Oleynichenko for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 133, theoretical physics. Is titled Relativist Coupled Cluster Theory for Electronic States of Molecules with Several Open Shells. The thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University, issued August 5th, 2021, number 7813/1. Alexander Oleynichenko has prepared his thesis at the Lomonosov Moscow State University as a postgraduate student, as well as at the Konstantinov Institute of Nuclear Physics of NRC Kushadov Institute. And Alexander Zaitsevsky, Doctor of Sciences in Physics and Mathematics, leading researcher of the Faculty of Chemistry of the Lomonosov Moscow State University, is the thesis supervisor. Seven papers published in journals indexed in Web of Science and Scopus describe the research findings of Mr. Oleynichenko. And all the documents provided by the candidate for the degree comply with the requirements of St. Petersburg State University, and they are found in the certification file of the applicant. And curator of the defense, member of the Department of Dissertation Board Support, has all the copies of these documents. And before I give the floor to our candidate for the degree, I need to ask the members of the board, do you have any general questions to our applicant, and is there a need to read out all the list of documents that were provided by the candidate for the degree? No, no need for that. Okay, and as there are no questions, let's listen to the report of our candidate for the degree. Alexander, please, you have the floor. Good morning, distinguished chairman of the board, distinguished members of the board, and distinguished guests. I'm going to make a report on my thesis titled Relativistic Coupled Cluster Theory for Electronic States of Molecules with Several Open Shells. And let us start with the relevance of the work. Wide precision estimates of the electronic structure of atoms and molecules in excited states have such a paramount importance for contemporary theoretical physics, mostly because it's impossible to secure atomic and molecular spectroscopy without them, including spectroscopy of real-life molecules and elements. And multiparticle theory of electronic states of molecules and atoms allows us to compute coefficients of amplification of P and PT odd effects. And these coefficients cannot be secured otherwise. And therefore, thus, this theory, multiparticle theory, becomes an integral instrument in order to interpret the results of our experiments for new physics. And I should mention also the study of matter in ultra-cold state. And in near future, I believe that the approaches that we developed in the thesis will be used for cluster modeling of local processes and impurities in solid states, in solid bodies. And among all the modeling technologies, the most promising basis for future models of new generation is the relativist method of coupled clusters in Fock space. It is rather simple and pretty accurate, and even more, it provides for a systemic approach to the establishment of approximations with a higher accuracy. But still it has a range of limitations, in particular the range of modeled states provides for states with a maximum 2 open shells, 2 electrons on closed shell. And up until recently, this method was not applicable to compute the transition states of molecules. And we can say that regardless of all these decades of the development of the method, its accuracy is still lagging behind from the needs of contemporary spectroscopy experiment. And the described difficulties allowed us to voice the goal of the thesis, that was to expand the opportunities and the range of applicability of relativist theory of coupled clusters, and to secure application to the modeling of the systems of contemporary physics. And here you see the structure of the thesis. Here we have 4 chapters and appendixes. First of all, the basis of formalism of operators and a short review, and we also describe new program XPT here in this chapter. In chapter 2, the major attention is given to the development of the method for systems with 1 or 2 uncoupled unpaired electrons, and consideration of triple excitations. This work for 3 electron systems is continued in chapter 3, and 4th chapter is dedicated to the calculation of matrix elements, including non-diagonal matrix elements and characteristics of transitions. And we use molecules of dimers of alkaline metals. Initially, let us remember the coupled cluster method. It is based on the formalism of effective operators in the wording of Bloch. And Schrödinger equation is reformulated in a small subspace with finite dimensionality, namely the Schrödinger equation turns into the Bloch equation. It's given here to the right. And the resolution of the problem is in finding effective operator, that's omega, and model vectors. That are the projections of exact solutions and wave functions on the model space. And if we find the wave operator, we know everything in the system. And we know its levels of energy. And in the coupled cluster method in Fock space, the wave parameter is parameterized by a normally ordered exponent. And here T defines wave operator. And wave operator, as given here on the slide, can consist of summands of different particularity, 1 or 2 particles, and depending on the summands that you have, you can get different approximations. For example, this popular CCSD approximation that includes single and double excitations. And within the framework of this work, we perform the implementation of the method with full accounting of triples as well. So that's letter T from word triple. So that's how we compute. We start with a closed shell, and stage by stage we add up electrons, establishing model space from determinants with a specific number of holes and particles. And the determinants, we are talking about determinants with a specific number of holes and particles as determinants that belong to one Fock space sector. And sectors with 3 and more quasi-particles are titled as high sectors. For example, if we want to describe the state of 3-electron atom with 3 non-coupled electrons in vacuum, we're going to use this sector 0 holes, 3 particles. So that's it. And what are the models that we considered within the framework of this thesis? First and foremost, we carried out full accounting of triple excitations. That's model CCSDT in all low sectors and in sector on 3 particular particles sector. That's quite a demanding model for computation. Therefore, if we want to use it for huge systems and molecules, we need to reduce this computational complexity. Therefore, we simplify the equations a bit, getting -2, -3 models, STD -2, -3 models, -1 model. And with 3 particles, this CCSD method provides for the amplitude that is inherited from lower sectors of Fock state. And new amplitudes here are not established within the framework of this model. Therefore, we can expect that high accuracy can be achieved within the framework of CCSDT model, with triple excitation amplitudes are established fully from scratch. And these methods are quite demanding, labor-intensive, and quite frequently equations include hundreds of Gaussian diagrams. Therefore, we decided to devise a brand new implementation for the method that would be efficient, that would meet all the requirements, current requirements, and capacity of contemporary computers. Therefore, we carried out software implementation, XPT, duty-bound cluster method. And here, a key peculiarity is that it provides for the opportunity to carry out simultaneous computations at supercomputers and state-of-the-art stations. And now let's consider the specific results of work and the results of numerical modeling. And let us start with a double states. And let's consider thallium. So here, and plumbum atom. So you see that CCSD model does not allow us to get results with accuracy that exceeds 100 of reverse centimeters, and that's the fundamental flaw of the model. and it is fully explained by the absence of accounting of triple excitations. And if triple excitations are taken into account, this is the error here in the green column. The accuracy grows by an order nearly, and we can say that at the current point, these calculations are the most exact in the world for the atoms of non-alkaline metals. And that's thallium H molecule, and its electronic states are described by two particles over closed shell. And for the first excited state we see the spectroscopy constants. You see internuclear, distance, and thermo. You see that CCS-DT model gives good accuracy that is sufficient to plan experiments on precision laser spectroscopy. And what's important here is that error makes up 150 reverse centimeters, and for this molecule, that's much larger than, much smaller than needed. Therefore, spectroscopists can perform quite accurate calculations. And that's 3 electrons over a closed shell. That's lanthanum. A low-lying state of lanthanum atom secured by the distribution of 3 electrons across S and D shells. And on histogram, blue is the error of CCSD method, and green is CCSDT error. And we see that model CCSDT suits quite well for preliminary assessments, but the method cannot be seen as precision, and only CCSDT with full accounting of triple excitations is more accurate, because there the error is less than 200 reverse centimeters. And 2 other goals to compute the transition moment in rubidium cesium. The molecule is interesting because it's used in the synthesis in ultra-cold states, and the synthesis goes through the mixed spinor orbital interaction. You see it here below, and from this states complex we have band transitions into excited states, low-lying triplet sigma plus. And previously we did not observe these transitions, and using the calculations that we carried out in our work, we observed this transition experimentally. It was interpreted, and on the slide to the right you see the computed vibronic spectrum for one of the transitions, and you can see good coordination of the calculated data with experimental data. And experimental data is in this white columns, and theoretical calculations are black spots. And we also need to study superfine interactions in potassium cesium. And these calculations are quite in demand among experimenters. In potassium cesium we have 2 magnetic cores, and magnetic structure from cesium core is much larger than potassium core, so we can consider it during the first approximation, neglecting quadrupole interaction with superfine interaction. And superfine structure is most important for first 2 electronic states that are at the dissociation margin, and they are quite mixed here with superfine interaction. There were a lot of questions to this molecule. What is the character of interaction of matrix elements from intermatrix distance? Can we see it as permanent with large R's? And the dependence of the distance is the simplest example of chemical shift of the so-called frame characteristic. So that's the characteristic that is defined by the wave function behavior near heavy nucleus. And that's what we got, this dependencies of STV from inter-core distance, and this data was received for the first time. We see that matrix elements do not depend on R in the area after 8 angstrom, and in chemical sector, this deviation can make up 15% from the atomic values. And above all, in the thesis, we demonstrated that frame correlation and valency frame impact has the following influence. And here we should consider the restoration techniques in the frame as well to compute the characteristics. And this graph allows us to make the following theoretical prediction, that superfine split of rotational line will grow with an increase of fluctuation quantum number. Here you see our forecast in blue, and our colleagues from the Latvian University, that's Arvin's Ferber group. After our publication, they carried out an experiment, and in fact, our theoretical predictions were supported experimentally. These data for alkaline dimers were received for the first time in the world, and they have now similarities. And here you see the provisions brought for the defense, and I'll shortly read them out. So it was demonstrated that full accounting of triple excitations in low sectors of Fock space allows to approximately by an order reduce the error of calculations of energy of transitions and potentials of ionization compared to a double model. In triple sector, these models are not enough for precision calculations, and you need to include triple excitations fully. The methods of coupled clusters devised in the work allowed to experimentally observe vibronic shifts of low intensity and interpret them. And for molecule potassium cesium, we got very accurate data on superfine interactions in this molecule. And we demonstrated that the chemical shift of STV is defined by relaxation and correlation of valency electrons. And that's the list of publications given on this slide. And the next slide, the 7 articles that are included into Web of Science and Scopus databases. And these are the results of the thesis that were tested at different Russian and foreign conferences and at different workshops of Moscow State University, St. Petersburg State University, and St. Petersburg Institute of Nuclear Physics. So that's a list of conferences that I attended. And now let me thank you for attention, and I'll be happy to take questions if there are any. Thank you. Thank you so much. So, any questions to our applicant on the report, on the thesis? 2 minutes per question. Okay, if there are no questions, let us listen to the reports of the board members and to the assessments of the thesis. And then we're going to listen to some external reports if there are any. And our candidate can answer the questions at once after each speech, and that's what I offer, to answer the questions after each review. So, okay. As all the reviews were already published on the St. Petersburg State University website, I offer just to read the basic provisions, questions or remarks that you have. Do you support this idea? No objections about that? Okay. So, your reviews. Let's go along the list, and I'll be the last one. And now I would like to give the floor to Ivan Andreevich Metropolsky. Thank you. That's a pretty good thesis. I liked it a lot. I'm not an expert in the field, though I'm a theoretical physicist. But I really enjoyed reading this work. Indeed, that's a pretty good work. That's a very good example for the next generations. When people ask how to write a thesis, you can show this work to them. I have no questions on the content of the thesis. I have just some negligible remarks. That pays no interest. And in my review, I mentioned the relevance of the work, and I emphasized that I really liked the field because that's not relying on supercomputers, but that's the use of your brain in order to ensure good calculations. That's the change of algorithms and change of theory of the issue. And as for scientific novelty and practical value of the results, I also mentioned them as well. And as for the level of result and the scope of study and publications, the thesis is significantly higher and better, significantly higher than the requirements to a PhD thesis. And overall, the thesis by Alexander Oleynichenko, titled Relativistic Coupled Cluster Theory for Electronic States of Molecules with Several Open Shells, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University, and Mr. Oleynichenko deserves the academic degree of the candidate of sciences in physics and mathematics and specialization 133 theoretical physics. And Articles 9 and 11 of the above-mentioned order are not violated. I have no questions or remarks. Thank you so much, Ivan Andreevich. Okay, thank you. Now, I'd like to give the floor to Professor Petrov. Alexander, do you hear us? Yes, we can't hear. The microphone is turned off. So, do you hear me? Yeah, yes, we hear you. Well, the goal of the thesis was to develop the method of coupled clusters in Fock space and the consideration of triple clusters and expanding the range of applicability for high sectors. And the relevance of the work is associated with high demand for such studies and calculations of the electron structure, including relativist and large molecules. We heard it in the report. That's the search for new physics and laser cooling of atoms and the characteristics of super heavy elements, and this list can be continued. It's clear that these calculations are quite in demand. Therefore, the relevance of work is not questioned at all. And it should be mentioned that the goal of taking into account such development of the method is super ambitious. And regardless of that, Alexander coped with it at a very professional level. He drew the formulas, he created a software program, and it is openly used already at St. Petersburg State University, Moscow State University, and St. Petersburg Institute of Nuclear Physics, and at other places as well. And he considered a range of examples. I won't read out the detailed content. He carried out test calculations that confirm the accuracy of the formulas and software. Therefore, the conclusions of the thesis are quite valid and substantiated. And it should be mentioned that the program is tested by a lot of people. That confirms its accuracy once again. And I would like to mention that the program exceeds the range of applicability of Dirac that is written by many people. And the range of applicability coincides, and it outbids Dirac in speed. Therefore, I believe it should get the highest possible mark for that. But there are certain comments. For example, the author draws conclusions that we heard today that seem quite natural. And we heard them all. that CCSDT method should exceed a CCSD method by an order, and the thesis provides certain examples in tables 2.3, 2.4, and CCSDT method there does not show to be that is more accurate than CCSD. It is not commented in the thesis, therefore I wanted to solicit your opinion on the fact. Yet another general assumption that we know that is the method of compound cluster is working. It is believed that it's better than the method of configuration interaction. And in table 3.3, the author gives calculations for pH molecule. And there, this method is comparable to the method of coupled clusters. And this method of coupled clusters in high sectors, that should be mentioned. So I wanted to get your comment on the accuracy of this coupled cluster method compared to configuration interaction method, considering all the amendments. And so the last question was about the calculation of constants for the structure. The author studied the dependency of state for potassium cesium, and he drew a conclusion that at long distances you can neglect the dependency on the distance for the constant of quantum structure, and this provision is already studied in different projects for ultra-cold temperatures. But such calculations, as Alexander emphasized, were not conducted before, and they have the same result. And having these results, it would be nice to assess how the change of distance of superfine interaction is different from exchange interaction or the interaction of spin orbital of second degree. And it should be mentioned as well that all the above-mentioned remarks do not compromise the overall high value of the thesis, and the thesis by Alexander Oleynichenko titled The Relativistic Coupled Cluster Theory for Electronic States of Molecules with Several Open Shells meets the requirements of the order. As of September the 1st, 2016, number 6821/1 on the procedure of granting academic degrees at St. Petersburg State University, and Mr. Oleynichenko deserves the academic degree of the candidate of sciences in physics and mathematics and specialization theoretical physics. And Articles 9 and 11 are not violated. So that's it. I have several questions in it. Yes, Alexander Nikolaevich, thank you so much once again for this attentive work with the text of the thesis and for the accurately formulated questions. And I'll go step by step. So the first remark on the fact that in tables 2.3, 2.4, especially in 2.4, I give the data for energies of excitations of potentials of ionization of molecular CH plus ion, and indeed we can see that in some states the model with full accounting of triple excitations, CCSDT, works worse than CCSD model that is quite lighter. So why? The coupled cluster method works quite well only if it's applicable, and its applicability surely is fully defined by the model space that we use. And in cation CH plus, we have 5 electronic states given in the table, as far as I remember. And for the first 4, the error of CCSDT model is 5 times less than for CCSD model. So here the order is correct. We make the result more accurate. And for the last state, C large, a singlet sigma plus, we get an answer that is nearly approximately the same. Why? because in the model space in calculation we did not include the configurations of 4 sigma orbital of the model, and such determinants introduce of significant contribution to this C-large state, up until 30%. And it turns out that here the model space is not sufficient in order to get precision results for this electronic state. And this situation was quite characteristic for the plumbum atom. You can see that the last state describes much worse than the previous ones. That's because in the active space we did not include CS orbital of the plumbum. And accurate results of CCSD for INCH+, for example, for this state A large singlet plus, we should consider when CCSD provides good accuracy and small errors, such situations should be considered as a good hit. And as for the second question, that's comparison and accuracy of the method of clusters and configuration interaction. Currently, it's rather hard to make some accurate assumptions here regarding the accuracy of the method in high sectors. These pilot launches that were performed, they were pilot just to test the new method and to consider what it can do. And certainly here we will need a lot of additional studies. This work has just started, but we can see that this method of coupled clusters, where it's applicable for heavy elements with a large number of electrons, it would be more accurate than the method of coupled clusters because it has the dimensionality coordination characteristics, and for CH we have less electrons, correlated electrons. And second is that in the article that I described in the table, there was a different set of zeta qualities, 6 zeta qualities, and here we had 5 zeta qualities. So that's a question to the basic set, first and foremost. And regarding your last question and comment on the comparison of superfine constants with exchange interaction in potassium cesium with an effect of spin orbit of second degree, I fully agree with your remark, Alexander Nikolaevich, and certainly such assessments will be performed during further studies because they are really in demand by our spectroscopy colleagues, experimenting scientists. And overall, we can say that we have everything to carry out these calculations, but we need some additional computing and studies. Okay, thank you so much. Alexander, are you satisfied with the answer? Yes, fully. Okay, Professor Kozlov. Well, I agree with my colleagues. I was really pleased to read this thesis, and I really believe that it can be recommended as an example to the forthcoming PhD students that need to write a thesis. The relevance of the topic is not questioned at all, and I wanted to mention that maybe in the previous decades we observed vigorous growth of precision atomic methods, and when cooling methods for atoms emerged and experiments with atomic traps, it led to a drastic rise of accuracy of atomic experiments and the emergence of new fields of study, including the application of atoms for fundamental studies. And right now we see the same for molecules. We see the drastic growth for the of experiments for the cooling of molecules, and we see the rise of accuracy of molecular spectroscopy and molecular experiments. And this leads us to the development of new fields of study of applicability of molecules in fundamental and in applied studies. And therefore, we see the demand for theoretical support of all these processes. We need calculations, precision calculations, the calculations of characteristics that cannot be directly checked experimentally, especially when atoms and molecules are used for fundamental studies. And we don't know the answer in advance, and we don't know what we're going to get as a result of experiment. Therefore, we should be based on reliable theories. And therefore, the relevance of such studies, as described in the thesis, is not questioned at all, because that's quite a timely study. The quality of work, to my mind, is quite high, and indeed the results are achieved at the top level, global level. And I'm sure that what Alexander did in the thesis, his results will be used further on by himself and by other researchers as well. So it seems to me that that's an example of pretty good work, both relevant and the work that is quite in demand. And the work does not just propose novel methods, but it also provides specific calculations. It shows the advantage of this method, and it shows its high accuracy and reliability, and the results were obtained at record level. So it seems to me that I have no doubts about it, that this work really deserves the award of the degree and very high mark. As I'm working in this similar field with similar studies, I was really interested to see these practical results, not just from the practical position, but also from the point of view of applied science. Therefore, I have several questions that are quite specific and maybe technical. So I drew attention to the similar tables that were mentioned by the previous speaker, therefore I won't dwell upon them. I already got the answer for that. And I have two questions that I wanted to ask you. So these are the technical questions, so to say. In your work, you pay a lot of attention to these triple excitations and the appropriate cluster amplitudes. And there you make an assumption that there is exponential dependency of amplitudes from energy denominators, and therefore you make a selection. You offer to drop some of them and to preserve the others, and you give a table where these matrix elements are showed with their dependency of denominators, and you make an assumption on the exponential dependency of them from the denominator, that they drop significantly with the change of denominator. And when I look at the images, I don't see this dramatic exponential dependency. Therefore, I wanted to get your opinion on the question. And yet another technical point associated with the specific calculations that we carry out in our group. Here in the thesis, you make an assumption on the choice of basis orbits and orbitals. And you say that when you shift from canonic to non-canonic orbitals, the error grows in all cases. And that seemed not grounded for me, and it contradicts our experience because we see non-canonic orbitals. And our experience shows that they work pretty well. So that's why I wanted to get your comment on that as well. But these are the technical remarks. They do not compromise the overall very good impression on the thesis. And I believe that thesis by Alexander Oleynichenko meets the requirements of the order on the procedure of granting academic degrees in St. Petersburg State University. And I believe that Mr. Oleynichenko deserves the academic degree of the candidate of sciences in physics and mathematics in specialization 133, theoretical physics. And I, as Ivan Andreevich, found no violations of Articles 9 and 11. Thank you so much, Mikhail Gennadievich. Mikhail Gennadievich, I prepared short reports to your comments. So as for the first remark on the exponential dependency of the amplitudes, indeed, I cannot but agree with you. And this formula 2.4 on page 58 is a rough assumption, you know, and it's just the first attempt to formalize this rather obvious fact that all the that the weight of excitation on this appropriate cluster amplitude should drop with the rise of energy of excitation, and this assumption is partially confirmed by visualization of the distribution of amplitudes on image 2.4. However, as you mentioned it quite correctly, this dependency should not and cannot be so simple as we wanted to see it. And the significance of the amplitude is not necessarily defined by their absolute value. For example, the contributions of double particles are defined by their integral. So therefore, we should consider it as an assumption. The problems defined in this section need additional careful study, and we need to take more complex objects than simple light atoms and molecules that were considered here. And as for your second remark, once again I agree with it, because my wording in the text is more categorical than the results allow in table 3.1, that's page 89 of the thesis. But overall, this observation that I made, that is mentioned in the text of the work, it is performed for ionization potentials in sector 1 particle for CCSD, CSDT minus 1 for excitation energies in this sector, at singlet S for CCSD model, and in 3-particle sector for the ionization potential and energy excitation energy in CCSD and CCSDT models. For some states, this assumption is true, and canonical orbitals work better for the range of cases. But there are deviations as well from this simple observation. And sure enough, the problem that you defined requires further elaboration, because essentially the practical interest of this study is quite immense. So that's a question of how we can try to win something, to win certain accuracy using other orbitals. Certainly this work will continue in the near future. Thank you. I satisfied with the answers? Yes. Okay, now I would like to give the floor to Vladimir Yorokin. Well, I'll shortly define the key points of my review. The review can be seen on the website. And I would like to mention that, first of all, it's important that relativist method is developed that is applicable for heavy atoms and molecules with heavy atoms. And in particular, it is applied to describe matrix elements of operators that are chosen at short distances near the cores of heavy elements, and that's a very difficult task, very difficult problem, and you need to take into account relativist effects and the effects of electronic correlation. And the results of the thesis coincide, are divided into 3 blocks, and the first block is dedicated to the implementation and the development of coupled cluster method with full accounting of triple excitations for atoms and molecules with 1 or 2 electrons or holes in the valence shells. And its implementation allows to improve the accuracy of calculations by an order compared to the accounting of single or double excitations. And the results are quite impressive for thallium and plumbum atoms. The second block is the summarization of the method of coupled clusters for the systems with 3 electron holes, and that's needed for the calculation of molecules and atoms of early actinoids that are quite relevant. The third block is a summarization of coupled cluster method for the calculation of matrix elements from electronic operators to compute the probability of electronic transitions and what's important for the calculation of frame operators like superfine structures. Then the relevance of the thesis is described, it was discussed. Certainly it's not questioned. At all. The validity of the results is quite high, and the coordination with existing calculations is present. And I would like to support my colleagues, saying that this thesis is performed at a very high level, global level. The scope of work is simply colossal. Such projects are carried out by teams of authors, and the fact that it was done by one person only basically is quite impressive. And as it was mentioned before, I want to point out the high quality of the text of the thesis. It's very concise and accurate, and it's really pleasant to read. I have 2 wishes rather than remarks here. The first one is that in the work you carried out the analysis of different methods of partial accounting of triple excitations. And basically that's an important topic because it allows to save computation resources, and this is done for energy. And it would be nice to test it for a superfine split as well, because to my mind the conclusions can differ because energies are taken at rather large distances and superfine split is taken at rather small distances. And the second point, the second question is a finite difference scheme, it would be interesting to discuss the applicability field of this method. For example, we have two closed states that covered by this perturbation. In this situation, is it this finite difference scheme, I believe, may not be applicable, and maybe I'm mistaken. But overall, these remarks are quite negligible, and they do not make the situation worse anyhow. And finalizing, I would like to conclude that the thesis by Alexander Oleynichenko meets the requirements of the order, the procedure of granting academic degrees at St. Petersburg State University. And Mr. Oleynichenko deserved the academic degree of the candidate of sciences in physics and mathematics and specialization 133 theoretical physics. And Articles 9 and 11 of the above-mentioned order are not violated. Thank you so much, Vladimir Anatolyevich, for the kind words and for the remarks that you've given, and I'll answer them. As for the first remark, that's about the analysis of triple excitations. Overall, the application of the approaches that we developed to describe framework characteristics is quite a popular topic, and it's the field of further studies in the near future. And I cannot but mention the recent work of Leonid Skripnikov, that is here with us. And this work was dedicated to calculations of gradient of the electronic field in the bismuth atom. And it had a goal to exclude this quadruple moment of bismuth core from experimental data. And it's rather hard a problem, and it's hard because the electronic state of bismuth, both basic and excited ones, are formed by the distribution of 3 electrons along p orbitals, 6p orbitals, and the static correlation is quite strong, and you can not resolve this problem in any other way than coupled cluster way. And Leonid demonstrated that the counting of triple excitations ensures good result. And here the contribution of triple excitations made the impact of 3.5%, and that's quite significant. And as for magnetic dipole interaction constant, such results were not obtained for them, but I hope and I plan to study this issue in more details further on. And as for the second remark regarding the applicability of finite difference scheme, indeed you are right to say that this scheme does not work when we study matrix elements between 2 states that are close in energy. There's several reverse centimeters. In this case, we have numerical instabilities that are impossible to overcome, and you can't find the matrix element. And in the thesis, we have this situation observed for states. I'll show you on the slide. For the states in the right curve, that's 0 minus and 1. And between them, in energy, we have 5 reverse centimeters crack. And matrix elements between these, it's impossible to get matrix elements between these pairs, but they can be assessed using different technologies. and we did not want them here, really. But still, this problem is in place, and that's a fundamental limitation for the method. And we just need to hope that in the future we'll find approaches that would allow us to overcome the problem that you outlined. Thank you. I'm fully satisfied with the answers. Thank you. Okay, now I would like to give the floor to Alexander Trofimov. Distinguished members of the board, distinguished colleagues, first and foremost, I would like to thank the board, the candidate and his academic supervisor for this honor to be the member of the board at St. Petersburg State University, and also for the opportunity to get acquainted with a really fascinating and outstanding thesis that is quite close to my academic interests in my field of study. The relevance of the thesis a relativistic coupled cluster theory for electronic states of molecules with several open shells is explained by the growing interest of the role of accurate non-empirical calculations of electronic content and spectroscopy characteristics of compounds with heavy elements. And such calculations are in demand due to various studies in contemporary experimental physics, including laser cooling of molecules, experiments on the search for interactions that violate parity, and spectroscopy of super heavy short-life elements. Above all, these calculations are needed in the context of the development of new optic technologies and materials, and based on organic complexes. And here we are talking about organic light diodes. And the calculation methods should respond to several requirements that are hard to combine. First, they should take into account the relativist effect. Second, they should take into account the correlation effects. And third, they should be applicable in case of high density of electronic states and configurations with several open shells. And it should be mentioned that the development of such methods is quite a challenge for contemporary quantum theory of molecules, and is one of the most acute problems that are still unresolved. And that all makes the thesis quite important, and gives it priority both for theory and practice of physics studies. And the novelty, theoretical and practical value of the work, I believe we can see them in the fact that for the first time there was the transition to a higher step of methodology of coupled clusters in the Fock space on the level of approximation of CCSDT that took into account single, double, and triple excitations, which was previously unattained within the framework of the relativist theory. And the improvement of the accuracy of calculations for energies and characteristics compared to the previous approximation of CCSD changes the situation with practical calculations, making this method an important instrument of contemporary physics studies. No less important, from the practical and scientific point of view, is the summarization of the method for the case of three particles. And this expansion of theory makes it a whole range of configurations achievable, like systems with three shells, and that's quite important for the calculation of systems with the participation of heavy elements. And finally, in the work, he developed the methodology of calculated diagonal and non-diagonal characteristics operators based on different schemes that allows to use the coupled cluster method in different options to ensure accurate calculations of non-energy characteristics, starting with dipole moment of transition to the characteristics of magnetic dipole STV as it was demonstrated in the work. And finally, there's a need to mention that the candidate has developed his own software that is widely used, that is comparable to direct package, and even now it is accessible for a broad range of users across the world. And commenting on the thesis, it should be mentioned that chapter 1 of the thesis is a well-written and useful literature review. And here he considered different wordings of the method of coupled clusters, including the method for Fock space. And in this chapter, we see the description of program implementation of the method of bound clusters in Fock space. That is one of the central results of the thesis that was performed. And in chapter 2, he discussed different methods that take into account triple excitation, and we see the first numerical results obtained using the calculation of energy and ionization of atoms of thallium and plumbum, and spectroscopy constants for potassium hydrate. And at that, we see the demonstration of impressive level of accuracy of the method of CCSDT in Fock space. And the obtained results really coordinate well with the experiment, and once again they coordinate well with the fact that was already known based on a non-relativist option of the coupled cluster method. So the error in energies of excitation and ionization at the level of CCSDT scheme drops by an order compared to CCSD level. So overall, it becomes equal to 001 or 002 electron volt compared to 0102 for CCSD. And though this fact is not demonstrated in the work in a broad range of examples, but still for experts in the field, it is quite expected, and it is quite credible as well. And observation regarding the behavior of schemes with approximated consideration of triple excitations was quite surprising. It was not previously known for relativist theory that the transition to such schemes dramatically reduces the quality of the results. In non-relativist option, it does not happen that quickly, and perturbation methods are quite good an alternative for CCSDT. In chapter 3 of the thesis, he describes the approach to the summarization of FSCC method for the case of molecules with 3 and more open shells. And here the results, they improve the universal character of this method from the point of view of calculation of heavy elements that are characterized by the presence of electron structure with several closely lying configurations. And a good example here is the consideration of lanthanum atom with lots of electronic states, and there's good coordination of the computed and experimental potentials of ionization and energies of excitation. And I wanted to mention for chapter 2 and 3 that there's a very accurate approach of the applicant, and the drawing of equations was done using Brown technique diagram. And on the other hand, the developed programs were tested at several stages, and the logic and reliability of this testing is not questioned at all. And this adds up to the credibility of the results. And chapter 4 has the description of the developed methodology of calculation for diagonal and non-diagonal matrix elements of operators within the framework of SCC method based on finite difference approach, and the high demand for such theoretical data is seen quite well based on the successful cooperation of the author with experimental physicists. And in some of the works of the candidate, his data was used not just for the interpretation of the spectra of laser-induced fluorescence of the molecule of rubidium cesium, but also at the stage of preparation of spectroscopy experiment itself. And I can give you the following remarks here on the work. And the first of them is rather a question than a comment. In Thesis, maybe it would be appropriate to carry out the comparison of the developed approach of SCC with the approach of coupled clusters for the movement equation EOM-CC that is seen quite quite relevant. It can be implemented in a relativist approximation of CCSDT and its options IPEA, DIP-DEA could allow to carry out the calculations of systems with open shells. Second is that, to my mind, section 1.6 of the thesis dedicated to program implementation deserves to be described as in a separate chapter. It would be logical as well, because the major part of chapter 1 is literature review, whereas section 1.6 represents important results of the author. And finally, this short remark, in expression 4.6, there is a misprint. In the right part, you should have this overlapping integral between the states with indices n and m rather than m and m. But certainly these remarks are not dealing with the major results of the work, and they do not compromise the overall very high value of the thesis that I believe gives a huge contribution to the development of calculation methods in theoretical physics of molecules. Thus, the thesis of Alexander Oleynichenko on the topic titled The Relativistic Coupled Cluster Theory for Electronic States of Molecules with Several Open Shells meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And Mr. Oleynichenko deserves the academic degree of the candidate of sciences in physics and mathematics in specialization 133, theoretical physics. And Articles 9 and 11 are not violated. Thank you. Thank you. Alexander, please. Thank you so much, Alexander Borisovich, for such a detailed review, for your questions, for your comments. As for the first remark, on the equation of motion, CC. Indeed, this methodology is actively developing today. It is actively used. But when we launched our work. That was spring 2017. We had no relativist implementations for this method. They did not even exist for molecules, and this realization was carried out simultaneously with us by a team headed by Andrei Gomes. And it was included into the direct package. It was well tested in the year 2021, several months ago. Therefore, performing such comparisons for relativist problems was impossible. But the actual equivalence of approaches for the equation of movement and for the coupled clusters in Fock space in low sectors. So this actual equivalence allowed us to carry out the testing of the accuracy of the developed program. Because the results of non-relativist calculations at FSCSDT, so these results were compared to the results that were obtained within the framework of movement equations by the team headed by Monica Missel. And these results were obtained in 2010, 2009, and they were published. And one could compare our excitation energy with the calculations of Missel. And indeed, we had the perfect match of figures, and it allowed us to make a conclusion on the fact that our program worked correctly. And in chapter 3, we carried out the comparison with the equation of motion. It's hard to translate in the Russian language. That's triple electron affinity. That's TEA abbreviation. And it was shown that in case of using EO method, the error reaches 25%. The error of calculations. Therefore, it's completely inapplicable. And it's clear why it happens, because in this method we use linear operator of excitation that has an impact on the state instead of exponential one. So this EO method for 3 particles, it does not work, and it works rather works badly for 2 particles. And there's also the drawback of this movement equations for deep D, DEA models. An important drawback here is that there is no coordinated coherence, and it will show in systems with many electrons. And coupled cluster theory has no such problems. And as for interfering states, yes, it's true, because the mobility equation is based on the matrices of large size. In fact, from the point of view of numerical solution, that's a convenient goal. You get answers. But at that, the interfering states emerge at diagonalization along with the target ones. It's hard to detect them and to say something about the error. And essentially, the problem of interfering states is explained by these denominators that are close to 0. They're just a consequence of the fact that the problem is set incorrectly, and the projections of some target vectors on the model space prove to be quite small. Therefore, we have this large non-physical amplitudes that give us the collapse of the procedure using the Jacobi method. And in fact, this lack of coherence, it should be perceived not as an obstacle, but rather than a signal that a problem is set incorrectly. The second remark regarding the separate chapter for section 1.6. Yes, I could have made it, but essentially, the choice of place for appropriate section was explained by the need to stick to the coherence of narration, because in chapters 2 and 3 we have the discussion of computational difficulty of the developed models, and these conclusions are based on section 1.6. Therefore, the goal was to write the text like that, so that it would allow to make references to the previous sections and not to lose coherence. And as for the misprints, thank you so much, Alexander Borisovich. Indeed, I cannot but agree. This was a misprint, unfortunately. Okay, thank you so much, Alexander. Are you satisfied with the answers? Yes, thank you so much. I'm fully satisfied. Okay. Now I would like to give the floor to Mariana Safronova. Yes, it's really a pity that I can't attend the defense personally. The thesis was really amazing, and it was interesting to read it, as it is in the field of my study. The thesis is very important, and the topic is really important and relevant, because these exact calculations for molecules and atoms are quite important, because there are a lot of new experiments that are planned for cold molecules, for the search of electric dipole moment. There is a new experiment in Caltech as well for them, and for these experiments we need these calculations and calculations of different transitions, the calculations of interactions, and the methods developed in the thesis are of paramount importance to such experiments. Therefore, the thesis is really interesting. It is well written, and as many people mentioned, that's a good example of a wonderful thesis. And specifically, there are 3 chapters. There are 4 chapters. There is a very good introduction that describes the previous methods quite well. And essentially, this chapter describes the novelty of the thesis and developed programs, and the fact that the program was not just developed, but also it is accessible for other people that can use it. That is also a good contribution. And in the future, it would be nice to have this additional description of the program. And also, it's interesting that this program is now now working in parallel, and there are a lot of examples for thallium, for plumbum, for different molecules. And it should be mentioned that the work is exceptionally accurate, and different contributions are described. And it was really interesting to see the tables that described the contributions of at different levels of triple excitations. And this study of triple excitations, whether they can be included partially, that's a very important part of the thesis, because triple excitations are included into our methods as well. And it's hard to include them, and therefore it's important to see how we can partially make certain diagrams. Therefore, it was interesting to see whether the triple excitations number could be reduced without loss of accuracy, and this part was really fascinating. The results are quite good. The coherence is quite good with the experiment, where he described the experiments, and the demonstration that this method is quite accurate, and it can be used for many interesting problems. And my comments are quite short. One comment was that it would be nice to get a bit more information on the model space, because that's an important question. And it would be nice to learn something for the systems with potentials, and about the procedures, about how these potentials are used in triple excitations. And one of the comments was about the comparison of configuration interaction. In this case, it would be interesting at what level they are done, whether it's exact, how many excitations were performed and resolved. In a case, because there's a comparison with triple excitation, but in some examples it was interesting to learn whether the shells were frozen or not in the process. And in the future, maybe for future studies, it would be interesting to learn whether we can define linear and non-linear triple excitations, because that's important for the comparison with other methods. So the thesis by Alexander Oleynichenko, titled "The Relativistic Coupled Cluster Theory for Electronic States of Molecules with Several Open Shells," meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University, and Mr. Oleynichenko deserves the academic degree of Candidate of Sciences in Physics and Mathematics in Specialization 133, Theoretical Physics. Articles 9 and 11 of the above-mentioned order are not violated. And all my remarks certainly are just negligible, and the thesis is exceptionally high quality. Is of an exceptional high quality. Thank you so much, Mariana Sviatoslavovna, for such a detailed review, such a kind review, and I'm really grateful to you that you managed to find time to participate in the session. It's really pity that you're not here with us personally, but I believe it's not a hindrance for us. And as for your remarks, in all the calculations of coupled cluster method, we used quasi-full model spaces, and such spaces include all the possible determinants that are obtained during the distribution of all the holes and electrons on single particle states that are chosen as active. The more detailed description is given on page 27 of the Russian version. Then, in the thesis, for every of the problems, we have detailed information about the establishment of the model space. For example, for thallium and plumbum, these are pages 67 and 8. Thallium H, that's pages 73, 74. Lantanium, page 96, and so on and on. And as for the method of pseudopotentials, short review is given on page 36 in section 1.5. But it should be mentioned that the program that we use was initially described and designed as a molecular program. And the only thing it operates for the establishment of the structures of data that have integrals and amplitudes, the only thing that it operates is the table of non-given representations of able groups of symmetry. And using cluster method, it's not important for us whether pseudopotentials are used there or not. Certainly the number of correlated electrons is reduced for the number of electrons that go to pseudopotential, and thus no additional difficulties are found here. I would like to emphasize that's because this is a molecular program, and as for atomic programs, I believe we may have certain additional difficulties here. And as for the comparison with the full method of configuration interaction, in all the calculations, we considered all the configurations, and no additional limitations were introduced. So frames were not frozen, and we can say that this method, as methods described in tables 2 and 3, they are accurate answers for Hamiltonian in a set basis. So I believe that's basically it. Did I answer all your comments? Or... Yes, everything is okay, thank you. Okay, thank you. Then my review comes next. I'll read some parts. First of all, I would like to say that I like the thesis a lot, and it really sets a very high goal for the other thesis, and the developed method is more accurate for the calculation of the characteristics of molecules. And currently, numerical modeling of molecules is quite in demand, and it is used for the preparation of contemporary experiments and for the analysis and interpretation of experimental data. And for many most significant experiments, theoretical calculations play an important role, and record accuracy of the developed method and the demand for numerical modeling define the high accuracy and high relevance of the thesis of Mr. Oleynichenko. In the thesis, we have the solution to a very important problem, the implementation of Relativist Method, considering double and triple excitations. This goal is of paramount importance for the development of modeling systems and for the application of relevant problems in physics and for the search of new physics. The thesis is written quite well, and the revised methods are represented quite well, but there are several questions. First question, how did you take into account the braid interaction? Did you take into account the lagging? Second question, did you take into account the impact of the negative spectrum of the Dirac equation? Third question, what time and what computer resources were used to carry out the calculations using triple excitations and calculations described in Chapter 4? And the fourth question, it is interesting to learn your opinion about the major restriction for this method of clusters. And the conclusion, the thesis by Alexander Oleynichenko, titled Relativist Coupled Cluster Theory for Electronic States of Molecules with Several Open Shells, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And Mr. Oleynichenko deserves the academic degree of the candidate of sciences in physics and mathematics in specialization 133, theoretical physics. And Articles 9 and 11 of the above-mentioned order are not violated. Thank you so much, Oleg Yurievich, for the questions and remarks. And I'll go step by step. As for bright interaction, indeed, for all the systems that include the atoms of heavy elements, including lanthanum, thallium-H, plumbum, thallium, rubidium cesium, potassium cesium, bright interaction was taken into account, in fact, but it was taken into account effectively using relativistic pseudopotentials. It is possible due to the fact that these pseudopotentials were devised by Nikolai Mosyagin, and they were generated for atomic calculations that take into account bright interaction and lagging. These potentials were tested several times, and it was demonstrated that in order to take bright interaction into account, that is, by the way, free, these potentials work quite well with high accuracy. And the only exception here is atomic calculations that were carried out at the level of CCSD theory for thallium and plumbum atoms by Professor Ephraim Eliav from the Tel Aviv University. These results are given in Chapter 2, and they are used in Table 2.5. And in these calculations, regardless of the bright operator frequency, so this operator was used in Hamiltonian, was taken into account in the Hamiltonian. And as for the negative spectrum contribution to the direct equation, it was not taken into account within the framework of this work, and thus it is provided that for the use of no pair. So there is no approximation here. That's the approximation that we use in all the calculations. And the two last questions regarding computer resources and the major restriction for accuracy, they are closely related. Because essentially, currently the main restriction for the accuracy, main limitation for the accuracy, is an ability to use broad and full basis sets and calculations that fully take into account triple excitations within the framework of CCSDT model. It's clear that we can more optimize the program, but it's quite promising to shift from the atomic version, and such work is ongoing, and we are doing it together with the group of Professor Anastasia Barshevskaya and with Professor Efrem Eliav. If we have spherical symmetry, it's clear that we can reduce the calculation costs and use broader basis sets. And there's also a need to use the shifts of energy denominators, intermediary Hamiltonians in cases when interfering states do not allow us to get the solution at once. And there is also the error coming from pseudopotentials, and the shift to summarized pseudopotential will allow to minimize this problems later on. But as I've already mentioned, such a limitation of accuracy that is associated with computational difficulty of the method, I would like to give you certain figures here as well regarding the time of implementation of goals. Some test problems, carbon, nitrogen atoms, CH molecule, and its ion, such problems were chosen in order to spend from several minutes to several hours on their solution. So these are small test problems. And the real applications, like thallium, plumbum, lanthanum atoms, they required from 1 to 2 weeks of calculations, and from 1 to 2 terabytes of operative memory. So these are quite significant costs. And we used the Konstantinov supercomputer, and we used working stations and servers of the Department of Laser Chemistry of the Moscow State University. So overall, we can say that code optimization will follow, and this would allow us to scale up the opportunities to include functions in the basis, including high angular moments that are really of paramount importance if we want to get highly accurate results. Yes, and I wanted to specify. It seemed to me that you wrote that you used model potentials for traditional amendments developed by Shabayev. So you took into account the negative spectrum. Yes, certainly it was taken into account. But in fact, I used these results. So this part of work that you quote, it was performed in co-authorship with Efrem Eliav, and these calculations were carried out by him, and I wrote about it in the thesis. So yes, we took the contributions into account. Okay, thank you. Okay, thanks. I'm satisfied with your answers as well. So, distinguished colleagues, distinguished members of the board, is everyone satisfied with the answers that Alexander provided? Yes? Yes, okay. Now we can give the floor to people who are present in the room, who are not members of the board. That's Anatoly Vladimirovich Titov, head of the Department of Quantum Chemistry of St. Petersburg Institute of Nuclear Physics. Hello, Anatoly Titov, head of Lab of Quantum Chemistry. And it should be mentioned that these calculations, as soon as we performed a summarized pseudopotential method, so we were interested to compute everything with a couple of clusters, and Professor Ilyav launched these calculations along with us, but the problem was that for one molecule, we spent years for them. It was clear that it doesn't work well in order to efficiently calculate everything. We understood the difficulties, we tried to do something with it, but we did not manage to. So it was clear that that's really huge work and we don't have opportunities. And when Alexander said that he wanted to work with that, we understood that he does not understand all the difficulties, and that was sheer luck. We agreed with that, and we did not expect that he'll manage to modernize the program somehow. We did not expect that he will write his own program that will be efficient, and this allows that would allow to take just a month or several weeks instead of a year. And I'm really happy because it allows not just to resolve the goals that we resolve the problems that we used to resolve some previously, but now this program is used in other spheres as well, the spheres that we could not even imagine before. Okay, anyone else? No one, okay. Then questions that were submitted on the St. Petersburg State University website during that were submitted during the broadcast. Do we have such questions? None. Okay. No questions. So, Andrei, that's the thesis supervisor. Please tell us about the candidate for the degree and his work. Yes, thank you so much. Yes, this thesis supervisor term sounds quite strangely, because that's an independent researcher currently. Currently, he does not need any supervision at all. But still, during this work, I was the thesis supervisor. And indeed, we launched this work with Efraim Eliav in 2017. And practically from the very beginning of this work, Alexander became the engine of this work. And whatever he took, he became a professional in this sector. Not a single unprofessional step at every stage. And he's a highly professional physicist, and he's also a highly professional expert in IT. He has the second education, and he worked very quick. He had no problems with mastering certain neighboring fields. And what's important in this situation is that he is not allergic to organizational activities. he coped with it quite well, as he coped with everything else. So he's quite professional with that as well. So I have no doubts about the fact that he deserves the award of the academic degree of Candidate of Sciences. And that's basically it. I have nothing to add. And I was really pleased to work with him, and I hope that this work will continue. Thank you. Thank you. So, dear colleagues, anyone else willing to say something? No one? Okay, we stop the discussion and we stop taking questions. And before we draw the conclusions and before the final vote, I need to ask the members of the board the following question. Are there any questions or comments about the procedure of the defense, including this, the questions about the remote access? So I need to ask you all. Ivan, no comments. Okay, Alexander, no comments. Mikhail, no comments. Vladimir, no comments about it. Alexander, no comments. Mariana, no comments. Okay, I have no comments as well. Alexander, yes, no comments. Okay, next item in our agenda. The vote. Distinguished colleagues, before the vote, we have an opportunity to announce a break in order to discuss the results of the defense, and this discussion will not be broadcast. How do you think? Do we need such a discussion? Yeah, I believe there's no need for that. Yes, the situation is quite clear. Okay. Then we proceed, and now I would like to solicit your opinions. Personally, you need to voice your opinion. And currently it's 8 minutes to 1 p.m. So, distinguished colleagues, so let's check that we all hear and see each other. Yes, we do. Okay. Therefore, I raise a question on the award of the academic degree of Candidate of Sciences in Physics and Mathematics and Specialization 1 through 3 Theoretical Physics to Alexander Oleynichenko. And I would like to emphasize that voting for the award of the academic degree, each member of the board agrees that Article 11 of the order is not violated by the candidate, and I would like to quote it. So, in the thesis, the applicant for an academic degree is obliged to cite the author or the source of the materials or individual results borrowed, using the results obtained by the applicant personally or in cooperation. The applicant for the degree is obliged to note this circumstance in the thesis. And I would like to remind you that the decision on the award of the academic degree is positive, provided more than 50% of the board members, but not fewer than 3 people, voted in favor. That's in conformity with Article 17 of the Order on the Procedure of Granting Academic Degrees at St. Petersburg State University. That's appendix number 2 to the order is of September the 1st, 2016. So let's start the vote. Professor Metropolsky, what's your opinion? I vote for the award of the academic degree to Alexander Oleynichenko. Okay, thank you. It's enough to say that you just vote for. Okay, Professor Petrov, what's your opinion? I vote for the award of the academic degree. Then Professor Kozlov, I vote for the award of the academic degree. Then Professor Yerokhin, I also vote for the award of the academic degree. Then Professor Trofimov, yes, I also say yes. And Mariana Safronova, professor, yes, I also vote for the award of the academic degree. And okay, and I'm chairman of the board. Oleg Andreev, and I also vote for the award of the academic degree. So, distinguished colleagues and guests, I would like to announce that out of the 7 members of the board, 7 voted for the award of the academic degree, no one voted against, and no one abstained from the vote. Thus, we award the academic degree of the candidate of sciences in physics and mathematics and specialization 133 theoretical physics to Alexander Oleynichenko. And the finalizing remarks of Alexander. Let me thank everyone who gathered here for the full support. I would like to thank the members of the board, the chairman of the board, for their attentive work with the text of the thesis, for all the remarks that they've given, for the positive vote. And I would like to mention that the defense of the thesis is not an achievement of one person. That's an achievement that is impossible without dozens of people who helped me, who supported me at all the stages, without whom this work would be simply impossible. And I'm really afraid to forget anyone, therefore I beg pardon for that in advance. Therefore, I prepared a slide that I wanted to demonstrate. First of all, I would like to express my sincere gratitude to my academic supervisor, Andrei Zaitsevsky, for his contribution, for his support in the organization of this defense process. Andrei Veniaminovich, in turn, I hope that that we will continue our joint work, that it will be fruitful and successful, and I'm really happy that I was privileged to have you as my academic supervisor. And I would like to express my sincere gratitude to the members of the board and to my teachers from capital T, to Vladimir Yeryomin, Ulyanovskaya, Madam Pichugina, Mr. Khrustov, and I would like to express my gratitude to Mr. Petrov. I would like to express my sincere gratitude to Anatoly Titov and to Andrei Stolerov, without whom this work would simply be impossible. For many years they supported me, helped me, guided me in my work. And Anatoly Vladimirovich, Andrei Vladislavovich, once again, I'm really grateful to you for your contribution that is hard to overestimate. And I would like to thank our foreign colleagues as well. That's Professor Efraim Eliav from the Tel Aviv University, that's Anastasia Barshevskaya, and that's Erwin Farber and the Latvian team. And I would like to thank Lucas Vischer, because without his explanations it would be simply impossible to create this interface to the direct program. His words helped me a lot, and I would like to thank everyone who worked with me for this during this period of time. And in particular, I would like to thank Natalia Vladimirovna Karpova, Elena Naryshkina, and Tatiana Zakharova, and Elena Kraseva, who allowed to streamline all this process together everyone and to organize it that smoothly. Thank you very much once again, everyone, and I beg your pardon for forgetting someone, if I had. Yes, and certainly I would like to thank my family for the support, to my mom, Elena Vitalyevna, and to my wife, Anastasia. Okay, we congratulate Alexander, and I therefore close today's session. Thank you, everyone, for taking part in it, and turn off the broadcast, please.